Everybody. Hello, good afternoon, and let's get started with our session today. So as you know, today we're going to talk about repeated measures ANOVA, and it's an extension of t-tests, as we have discussed before. So some photos of some people that you have heard their names. One of them is Sir Fisher, and the other one is Gossett. He's the scientist who's behind the t-test. Student t-test is known as student t-test, but his actual name is Mr. Gossett, and he developed t-tests. Fisher is a person who is behind the ANOVA test, and it's nice to know them actually, just in case you want to know who has made your life easier in statistics. And Mr. Howard Levine, this is very famous because you know that the Levine's test is the person behind the Levine's test, and this is how his office looked like and how he worked. You see the computer in front of him. Yeah. Okay, and then we have the Welsh test. It's an equivalent to t-tests, but it's not exactly the same as a t-test. When your t-test does not meet the requirements of a t-test analysis, then you use a Welsh test. I mean, this is how he looks like. Okay. If you recall, we didn't talk in details, but Brown-Forsyth test is also another analogous test to t-test, and it can be used for comparing groups in terms of, for example, some scores like grammar score, etc. Okay. So before I start repeated measures ANOVA, I want to make sure if you have opened these two files or not. Do you have it open? This is one of them. It's called week 10. And the other one is also called week 10. Okay, so I assume that you have. Okay, so in order to understand what a repeated measures ANOVA does, let's recall what is it called? Paired samples t-test. Do you remember that? Here, I would like to show you the structure of the data, which is basically the same in both tests, both repeated measures ANOVA and the t-test itself, the paired samples t-test. On each line, as you see, number 1, 2, 3, you have measures for the same person. So for person 1, we have measure 1, time 2 measure, time 3 measure, and it can go all the way down. Here we only got 4 times. Time 1, time 2, time 3, and 4. Which means that time is our independent variable. And so we've got 4 measures over time. This is time 1. And interestingly, this is the dependent variable, this line itself, the data here. Okay, the data that you see I'm touching is the first time, that's dependent variable. The second part of the dependent variable is here. The third one is here. The fourth part is here. but the independent variable is time. Time 1, 2, 3, 4. Okay, so this is the independent variable. Remember this, because we want to measure the development of whatever variable it is over time. And we want to see if in time 1, things changed from time 1 to 2, time 2 to 3, 3 to 4. And if they changed, how they changed. Okay. So this is what I talked about actually. So let's just get started with the bare bone essentials. Imagine that you are teaching a class of whatever, grammar or English or anything. So you want to measure the development over time, whether they progressed from time 1 to 2, time 2 to 3, 3 to 4, etc. For the repeated measures ANOVA, you need to have at least 3 time points. Now, can you open your microphone and answer my question? What if you have 2 time points and you want to measure time 1, time 2 to see the development from time 1 to time 2? What do you use?
Pair sample t-test.
Exactly. If you have 3 time points, use repeated measures ANOVA. Now, as I have mentioned before, there are some assumptions for every test. And here are 4 major assumptions for the repeated measures ANOVA. One of them is independent observations. What does it mean? I go back to this data set. It means your first measurement, for example, this is the grammar score in time 1. This is the grammar score in time 2. You see the person who got 65 got 66 in time 2. Independence means that time 1 and time 2 scores were achieved independently from each other. In other words, it doesn't matter what scores you would achieve in time 1, your score will be independent from time. In time 2 will be independent from time 1. It's an assumption that most of the time is achieved. And there is no specific analysis for this. Some people would say you can run a correlation analysis, but it's not very common, honestly, to do a correlation analysis. Just theoretically, if you think that the test scores from time 1 to 2, 2 to 3, 3 to 4 are independent from each other, then you got it. That's it. So the second assumption is this very famous one, normality. Can you open your microphone and tell me how you measure that?
Skewness and kurtosis.
Can you explain more? How?
Oh, we just use descriptive statistics analysis.
Descriptive statistics. Okay, good. And how do you interpret skewness and kurtosis?
Skewness is between -2 to +2, and kurtosis is between -7 to +7. If they are in this range, then it's normally distributed.
Yeah. So that's according to some people, right?
Right.
Yeah, good. And you need to, if you're writing a paper, you need to cite who has come up with these criteria, and I have discussed that before. Okay, so the next one is sphericity. Now, if you're curious what sphericity is, let's remember the equality of variances. Do you remember that? Equality of variances in ANOVA, which we discussed.
Homogeneity of variances?
Or homogeneity of variances.
Okay.
It goes by both names, yes. So it's basically analogous to equality or homogeneity of variances in independent samples, independent samples ANOVA or factorial ANOVA. In repeated measures ANOVA, we use sphericity. Why is it so? Because we are comparing the variance of time of the differences between scores across times for the same person. It's defined in this way: the variance of all difference scores among test variables. They must be the same. So the variance of the difference scores, meaning that you need to calculate, and we don't want to do this honestly, but just to elaborate what I mean by this, you need to calculate the differences between time 1 and 2, and time 2 and 3, etc. And then find out what the variance of those differences are, and then find out whether the variances are more or less the same or very different from each other. That's the assumption of sphericity. Now, some names for you. There is a smart person, smart guy, called Mr. Mauchly or Mauchly. I've heard both pronunciations, but it seems that it's commonly used to say Mauchly. Okay, so Mr. Mauchly created this test to make our lives easier. I don't know if you agree with me on that, but that was his intention. So he created this test of equality of variances to investigate whether the variances of all the different scores among the test variables are the same or not. So this is the second thing. I mean, in addition to independent observations, let's just put it on the back burner. But in addition to normality, sphericity is the second thing that we want to investigate. Okay. So if we only want to compare scores across time, that's time 1, 2, 3, 4, as an example, we only have 2 assumptions to meet. These 2, normality and sphericity. But if we want to include, this is a between subject variable. It's not over time anymore. It's called between subject variable. Then we also need to include equal covariance matrices or equality of covariances. Now I'm going to get back to number 4 later. So I'm going to provide you with a skeleton of the analysis of repeated measures ANOVA, after which we will build up on that, and we will do the rest of analysis. Okay, so please open your data set. Let's start with this. Is it open now? I assume it is. I wait for a few more seconds just in case.
Yes.
Okay, good. So in order to run the analysis, you go to Analyze. If you have watched the videos and read the handouts, go to GLM again, repeated measures. I'm going to pause here so everybody is there. Click, and this window pops up. So by right, all of you must be here now. Okay. Now we have within subject factor name. Remember, within subject means that the person, like me, is compared with himself in time 2. And time 2 is compared with time 3. Is me against myself over time. That's why we call it within subject. That's within my own performance. It's different from between subject, something like gender, as you see here. That's between, because all people who are males are compared with females. That's between the male group and the female group. So here we've got within subject factors, and factor means independent variable. What do you like to call this factor? It doesn't matter, but here we've got time. Can you see that? So in order to, can you see in the SPSS file? So in order to be clear, I think it's a good idea to use time as our variable. Number of levels. How many levels do we have here, guys?
4.
4. Excellent. So you can include all 4, or if you like, you can just do 3. It's up to you. I would like to do to use 3 of them. I hope you don't mind. And then I'm going to add it here. Oh, this one should be removed. I mean, okay, so you're going to end up having something like this. Do you have that, everybody? Good.
Yes.
This is, again, this is because I only want to compare 3 time points at this time. Then I will allow you to compare 4 time points. So now this is a very simple step. Click define. This one pops up again. I'll reset it. So this is something that you should also be able to see. Do you see it? So I've got 3 time points. Time 1 goes to time. Oh, sorry. Time 1 goes to 1. 2 goes to 2. 3 goes to 3. That's it. So far, so good. We have a chat. Okay. Now, like I said, I want to provide you with a basic kind of skeleton for this analysis. So I don't provide too much details in the first round. Then I gradually build upon that. The first thing I would like you to do is a contrast. We can keep it as polynomial. It's always polynomial. And the best sort of analysis is a polynomial contrast. We have other types, but for repeated measures, it's polynomial. For non-repeated measures, like factorial designs, we could use simple analysis. So polynomial, continue. If you really like to have plots, I don't have any objections. So you can move time to horizontal and then add. That will be just good enough. The time's still there. If you move it to separate lines, you see it's not active, meaning that you can only have your variables on the horizontal axis. If there were 2 of them, you could move. I mean, you will see that later. Let's not just confuse you. This is good enough. And you don't need anything else. Click continue. Okay. Now remember, we used to do post hoc analysis, but it was only for a scenario in which we had a variable like gender, which was between subjects. Post hoc analysis can't be done if you don't have a between subjects, you see? There's no post hoc. So don't even bother to click on post hoc if you don't have a subject. So what matters here is you could get EM means. I'm gonna highlight both. Compare. Bomfroni. Why do I choose Bomfroni? Because it's better, because I'm comparing one time point against several other time points. We have repeated measures, so Bomfroni is good. So far, so good. Continue. Last session, I mean on Friday, I mentioned that you can save standardized residuals. I leave it up to you, is optional, but we can save standardized residuals. What do we use standardized residuals for? Do you remember?
For normality,
Can you elaborate? Yes, you're right. Can you elaborate?
to highlight the residuals and to check on the normality.
That's right. So we're going to get 4 additional variables, 1 per time. 1 standardized residuals for time 1, 1 for this, 1 for that, 1 for that. I don't mind actually, so let's keep it for the time being, and I'll show you how it works. Options. Well, we need to get estimates of effect size. Now, you know, I talked about sphericity, and I said it's analogous to homogeneity. But the term homogeneity of variances is only used if we have a between subject factor like gender. I need to move gender to this side, but I'm not going to do it now. I'll do it later. So if we click homogeneity tests, we will get an error message. Why? Because it's simply there is no between subject factor to use for the homogeneity test analysis. So we will get an error message. Okay, I'm going to leave it there so you'll see the error message. So that's sort of a prescient warning for you. Everything is ready. Okay. You see, my prediction comes true. Homogeneity specification is ignored because no between subject factors. Okay, so here, I think I'm gonna move this to a Word document, so I will explain it to you. Now, the first thing you need to look at immediately is this. Don't get yourself confused, please, and don't be confused by so many tables that you see in the output. What matters is, in the first step, is much least test of sphericity. So I'm going to copy this. Let me paste it into a Word document. Okay, can you see this, everybody?
Yes.
Nice. So the first thing we look at, it's examined like Levine's test of sphericity, but the p-value remains to be 0.05 here. Oh, this is a very ugly 5. Let me make it more interesting. Okay, good. Now, the first thing we need to look at is the sig or the p-value here. Oh, gosh.
Smaller.
There is something wrong with my, come on. Sorry, there is, oh no. Anyway, so the first thing we need to look at is the sig value. Can you see the sig value?
No.
It's smaller than 0.05, isn't it?
Yes.
Okay, so, okay, there, okay, good, we're back now. When this value is smaller than 0.05, it's smaller than 0.05. What does it mean?
Sphericity is violated.
Good. sphericity is not met. So this is the first thing we need to look at, of course, after normality. And I assume you have already looked at normality. So this is the first thing. So when it's not met, what should we do? We should remember, if it's not met, we should remember that the multivariate tests here, which are like ANOVA tests, are not reliable anymore. Okay, so we look at Mauchly's test or Mauchly's test of sphericity to find out whether we should rely on this table or not. Now, Mauchly's test says no, do not rely on the multivariate test. Just forget it. Okay, I'm going to forget it. What should I do now? Look at greenhouse geyser and Hohenfeld tests. So I'm going to go back to my table here. So this means ignore the multivariate tests. Okay. And it also means look at greenhouse geyser and Hohenfeld epsilon. This is how you write epsilon. What about them? We look at this and we look at that, but the most important one is this. So I give it 3 ticks, which means that when sphericity is violated, immediately look at this. Forget about everything else. Now, guys, how do we interpret greenhouse geysers test? I assume you have read the assigned papers and at least have gone through the slides. I'm waiting. Okay, here is how you look at it. If the greenhouse geyser test is small, if the epsilon is smaller than 0.75, then look at the greenhouse geyser. If epsilon is larger than 0.75, look at Hohenfeld. So just remember these 2, please. Don't forget it. So before you go to bed tonight, you're going to repeat this 100 times. If the epsilon is smaller than 0.75, look at the greenhouse geyser. If epsilon is larger, look at Hohenfeld. 100 times. So here, which one we should look at now? Look at both epsilons, preferably this one. Sorry? Greenhouse geyser.
Hohenfeld.
Okay, Hohenfeld. Good, good. Nice. Why is it so?
Because
Larger than
Larger than 0.75.
Excellent. So for this analysis, we're gonna focus on this. Because both epsilons, both this, and particularly greenhouse geyser, are larger than 0.75. Okay. Let me go back to my analysis. Now, so Marshall's test is telling us, look at greenhouse Hunefeld test, sorry. So here is what we need to look at now. This table. I'm going to copy it. Okay, so we should look at Hunefeld test. Hunefeld test is right here. Right here. Again, don't get yourself confused. Ignore anything else that you see in these tables and just put a laser beam focus on this because of this finding, which comes from here. Therefore, this. Okay, that's what you should do. Now look at this. The Hunefeld statistics. Can you tell me, according to the p-value, does it show that there is a significant difference across time, from time 1 to 2, 2 to 3?
Yes,
How do you know that?
because
P-value is smaller
P-value is
than
less than 1.
0.05.
Excellent. It's the same concept again. P is smaller than 0.05. What is the effect size?
17%.
How do you know that? What column gives you the effect size?
Partial eta squared.
Exactly. So you guys are learning well. Good. I hope all of you are following me. Nice. So partial eta squared is the effect size, and it shows 17.17% of variance in the data is explained by what?
By time.
Excellent. By time. This is what effect size means. Effect size. Any questions so far? Great. So you can ignore anything else and scroll further down to find estimated marginal means for time. Okay, it's like post hoc analysis. Question: when I move from time 1 to 2, is there a significant difference?
No,
How do you know?
because the p-value is larger than 0.05.
Excellent. Can you see that, everybody?
Yeah.
So when you move from time 1 to 2, there's no significant differences between the test scores of your students. From time 1 to 3.
Yes.
There is.
Good. Because
The p-value is
P-value
smaller than 0.05.
nice. From time 2 to time 3.
Yes, significantly different.
And that's because,
The p-value is smaller than 0.05.
what is the p-value again?
0.002.
0.002. Excellent. So you see, it's how you interpret it, and that's all of it. That's all. I mean, the most important things that we need to know about repeated measures ANOVA. Now, there's one more thing, of course, how to report it. This is how you report it. Please take a moment to read it. Okay. Question, why did we use this? Hohenfeld method, why did we use it?
According to Mochi test, the number is larger than 0.75.
So Mochli's sphericity was not met, and then you provide the p-value, and then you say that you applied a Hohenfeld method of correction. This is called method of correction. Okay, so that's what you need to write in your reports. And I have also gone through these. What I would like you to, okay, we will get back to this later. This is another example. Now look, F 2.094 is the degrees of freedom. In this analysis, because the greenhouse geyser is smaller than 0.75, can you see that? So we have used greenhouse geyser, although this is slightly above 0.75. So this is the first degrees of freedom. I hope it will not be too messy. Okay. And then we go to error, and we find the error of greenhouse geyser again, degrees of freedom, and it will be placed here. So degrees of freedom, this is how to report it. Okay, guys? So you need 2 degrees of freedom, 2 types of degrees of freedom. One is degrees of freedom from time, greenhouse geyser, and the other one is degrees of freedom of error time, or error whatever variable you have, and that will be it. Okay? The other thing you need to remember is, so what is the F value? The F value comes from here. You see they're the same. So I'm gonna do it. F value was the P value. P equals this. P equals this. Partial area square is this. Partial area square is this. That's how you write a report of your results. I think that's enough details so far. Yeah. So I'm going to put you in groups, guys. I'm going to have breakouts. And I would like you to go through the same analysis, but this time round, you're supposed to do 4 times. This is 3 times. So what you can do is click on time and remove it. And again, start from here, 4 levels, etc. So I'm going to put you in groups of 3. And you have 2 tasks. Evaluate the assumptions. Remember, I didn't evaluate one of the assumptions, which is normality. So evaluate the assumptions and then run the analysis Okay. After that, do the analysis and write a report, like one of those reports I showed you, like this, or this report. Okay, so that's going to be your task for the next 20 minutes. I'm going to put you in groups. Are you ready? Okay, everybody, welcome back. And I hope you have had a chance to run the analysis. What I'm going to do is to quickly run the analysis for you. Let me see if it's possible to shift things around. Okay, so I got to analyze. I'll do it first, then we will see what your problems are. Go to analyze, GLM, repeated measures. I need to reset it. I got time. I got 4 levels this time around. Define. There we are. I'm sure you have generated this. Now, time 1, 2. Oops. 1, 2, 3, 4. I'm going to move them together to the right side. So make sure that time 1 is in 1, 2 is 2, 3 and 4, they're consistent. It's brackets. Okay. Contrast. Do I need a contrast? Yes, polynomial. I'm going to explain it in this time round, by the way. Don't worry. And of course, you can have a plot. I want to have plot for time. This is a plot, and I'm going to explain that too. I don't need postdocs because I don't have a between subject variable. I need EMM. I move everything to the right-hand side, compare main effects, Bonferroni. Continue. Do I need to save? At this time around, I'm going to save standardized. Again, I'm going to tell you how to interpret them. Options, estimates of effect size. If you like, you can get descriptive statistics, but I don't need them for the time being. Okay so far? Okay. Now, this is the output. I don't go through the output first. I'm going to go back here. Okay. So if you look at your original data, you will see 4 additional variables that have been automatically created for you. Do you know what they are?
Standardized residuals.
Exactly. Do you remember that we can, let me just refresh your memories just in case you have forgotten that. Under save, I checked standardized. Do you remember that? This is what you will get, these 4 variables. So I'm not going to do it again. What do we do with this? We use them in normality analysis. So instead of checking the normality of the variables, I'm going to check the normality of the standardized residuals. Why? I explained this last session. Can you explain?
It's better.
It's what?
It's better.
Why is it better?
I don't know. Just you said the EM means and the residues are better than the previously introduced 2 methods.
Yes, good, well done. I'm gonna add on to it. In applied linguistics, we usually look at the normality of the main data. That's time 1, 2, 3, 4, for some reasons. But it's better, as you said, to look at the normality of the residuals, because it's actually the normality of the residual which is the assumption of ANOVA, not the normality of the dependent variables. But in many books in applied linguistics, they say, check the normality of the dependent variables. Ultimately, they're similar, but in some cases, they may give you different outputs. So my suggestion for you is to look at the normality of residuals. That's what I'm doing. This is step 1. Please do this for factorial design ANOVA as well. I talked about it on Friday. Watch the video again. It's exactly done in exactly the same way. Options. Skewness, kurtosis. That's what we need. That's all. Okay. Okay. So remember that I haven't gone through the results of my repeated measures ANOVA because I want to check the normality first. Is it normal or not?
Normal.
Normal.
Is anyone who doubts? Is there anyone who doubts that the data is normally distributed?
So,
Nobody doubts it?
do you still apply the same criteria?
We do, yes.
Okay.
So you think that it's normal?
Yeah.
I think it will be doubtful a little bit because the sample size is like exactly 13. But for skewness and kurtosis, we say like the larger the sample size is more applicable for skewness and kurtosis. But here we can see n is equal to 13. Yeah.
So do you have a different solution?
Maybe look at z value.
Sorry?
Z value.
Z value, how do you calculate it?
So if it is located in minus 1.96 and 1.96 to see if it is between this range.
Yes. Yeah, you're right. You guys are right. So you can divide the statistic here of skewness by its standard error. Please look at the slides of session 7.
Yeah.
And it should fall between minus 1.96 plus 1.96. In that case, we can say it's normally distributed. Now, in applied linguistics, again, not many people do that, honestly. So I would be okay. Many reviewers of your work will be okay if you stick with one of those criteria about skewness and kurtosis that I have explained before. So since both of these values fall between +2 -2 or -1 +1, or for kurtosis -7 +7, they're normal distributed. Is that fine? Okay, now I'm going back to the model. So the first assumption, tick. The second assumption, much least test of sphericity. What's going on here?
It's not met.
Sorry?
This sphericity is not met
Because?
because the p-value is smaller than
than
0.05.
0.05.
That's right. So what should I do?
Choose greenhouse gaser
Either
fraction. If it's
Yeah.
more than 0.775.
Sure. So I'm gonna copy and paste. So another one. Copy this, paste here. Copy, paste. Okay. So I'm gonna draw some lines here so everybody will follow. Okay. So yes, you're right. A much least test or much least test of sphericity shows that let me change the color, sorry. This is better. The sphericity assumption is not met. P equals, because I have the exact P, so I just write it down. 0.01, 001, oops. 001. Okay. Now, then, when it's not met, I need to look at the epsilon. Yeah, so here, the epsilon value is for greenhouse geyser, which I prefer to look at, is smaller than
75.
75. Good. Epsilon is smaller than 0.75. Therefore, I need to look at
Greenhouse geyser.
Geysers.
excellent, guys. Good. I need to look at this and ignore everything else for the time being. Now, tell me, is there any significant difference
Yes.
across the time points?
Yeah.
Yes.
Yes.
How do you know?
The p-value
Value.
is 0.005. It's smaller than.
Somebody's shouting. Is that happiness or?
Sorry, it's my daughter. Okay.
Oh, it's okay. I'm just kidding. Just wanted to joke. So, greenhouse geyser tells us, as you said, that there is a significant difference across time points. Now, I want to write down the F of what and what. I need 2 degrees of freedom here. Give them to me, please.
The first one is 2.094.
0.094.
2.094 and
Arrow time.
60.719.
This one.
7919.
Yeah.
error. Good, the amount of variance that's not explained. 60.719. Okay, equals. I need the F.
7.6.
7.6.
Exactly here. So you see there are 1, 2, 3. 1, 2. This is the third one. 7.664. Then p-value equals. It's better to give the exact p-value if you have it, unless it's very small. So
Yeah.
p-value equals 0.01.
0.
0 is missing there, sorry. 0.1. So partial eta squared. Please spell it out. At the interest of time, I don't spell it out, but you should spell it out. It's not a very good example set for you, but anyway. So partial eta squared is equal to
0.209.
09.
209. Good. So there is a significant difference across time. And now I want to figure out where that significant difference is. Now I come back to this later. I go further down to where?
Pairwise comparison.
Exactly. Pairwise comparisons. Now let's do pairwise comparisons. Is there any significant difference across any time points?
Yes.
In other words, look at this table, please. Okay.
Choose
You all should have this table. Do you? Can I check?
4.
Does everybody has this table?
Yes.
Yeah. 1, 2, 3, 1, 2, 3.
Is there anyone who doesn't?
3, 2, 4.
No. Okay. So I'm going to scroll down, and you're going to look at your table and tell me if these differences are significant. Time 1 and 2.
No.
What is the p-value?
Let me see.
1.000.
Yeah, so it's not
That's both.
significant. Time 2 and 3.
Yes.
The
Guys?
p-value equal to 0.042.
So your students' scores went down from time 2 to time 3. Hopefully this is something like anxiety for statistics. So they became less anxious as they went from time 2 to time 3. And that's statistically significant. Although they also had a downward trend from time 1 to 2, it's not statistically significant. But from time 1 to 3, how about that? Time 1, 3. Ignore 2.
Significant different.
Good. Time 2, 4.
Significant different.
There's a
3, 4.
significance.
Yes.
So everything is significant except for one.
1 to 2.
Yes. And you see the slope is not very steep downwards. It's a little bit less steep if you compare it with the rest of the slope. Now, look, the trend is like this. Okay. In statistics, just keep this in mind. I'm gonna go back to the last table that I didn't explain before. This is called test of within subject contrasts. I'm gonna copy it. Okay, here. And also copy this. Okay, guys, can you see it? Good. Now, in statistics, we have something called, and we don't talk about it really again. Sorry, just to keep saying we don't talk about this in this course. Remember the main objective of the course, to familiarize you with some of these analyses. And remember, in the past, there were not ANOVA or repeated measures ANOVA in the course. I decided to add them in because I feel that you really need to learn them. But there are other concepts like curve fitting, etc., that are really a bit more, they're a bit complex, if that's the right word. So we don't talk about it. What I mean by curve fitting is that you want to figure out the trend. When you have repeated measures, you want to figure out the trend. So you want to figure out if the trend is linear like this, or quadratic like this, or cubic like this. Okay. Of course, by eyeballing it, that's by just visual inspection, you can't figure out. I mean, you might say, I think this trend looks like this one. So it's more like a quadratic trend. But no, you should look at the p-values of them. So the p-value of linear tells you that there is a linear downward trend. So a linear downward trend, and the p-value equals 0.002. Now, it adds more value to your analysis. Why? Let me tell you how you can, and here is a good example, how you can provide explanations. Let me see, I had a very good sample. Sorry, where's the good? Okay, here's the sample I'm talking about. Across group, mean test scores follow a linear trend. Then, of course, you can provide the F values as well. I only provided the p-value, but you can provide the F in exactly the same way. You have degrees of freedom of 1 for time, then go down to error. This is linear, this is linear. So 28, then provide the F value, which is the same here, and the p-value. And if you like, you can provide the eta square, which is right there. So this is that is, the decline in the dependent variable maintains a similar rate over time. That's what it means. It has a similar rate over time because it's linear. The rate doesn't suddenly change. It doesn't have sudden changes. The rate is linear and therefore this almost the same, or if you will, similar over time. Okay, someone has pasted, yeah, Liziao has pasted the answer. Okay, guys, is it okay now? So in addition to, can you see, okay. In addition to that, here is what I suggest. In addition to the report that you wrote, you can also include this as a second part of the report. So what you can say is something like this. Okay, I'm going to put everything together so you will not be confused when you're writing your report. This is the first part. Of course, you should see if these p-values are correct or not. You should just replace them with the correct p-values, etc. And the other sample was, I'm gonna choose this one. Okay, so these are samples for you. Yeah, this is how you will write a, yeah, you see it was not met, so here is the follow-up analysis and then the rest of the story. So if you are writing a paper, sorry, or reading a paper, doesn't matter. But let's say you're reading a paper where the repeated measures ANOVA has been used. And my question for you is critique the paper's research methodology. You should look for similar statements in that paper. If you see that those statements or indications of these statistics are missing, then the paper doesn't provide you with all the information that it's supposed to provide. Next is you should also say here, continue with the results of pair-wise comparisons. For example, there was a, I decided to type it out so it will be easier for you to understand. Significant difference across all paired comparisons. The p-value smaller than 0.05. Oh, it shouldn't be. That part should not be italicized. I'm a bit meticulous when it comes to reporting statistics, except for time one versus, oops, versus, is that versus? No, versus time two comparison, provide the P. I mean, whatever the p-value is. Okay, this is a good write-up. Of course, what is missing is partial eta squared here. So you should provide that as well. Partial eta squared. Do you have that? Yes, here. You can report it. Partial eta square equals whatever. This is a classic systematic way of reporting the results of your ANOVA tests, which means that in the output of your analysis, you should be looking for these pieces of information. Okay, am I recording? Yes, I'm recording. Good. So it's on video too. Later on, you can pause the video and watch it again if you like. Okay, guys, so this is enough for now. I think we should take a break. After the break, we'll come back and we will continue the analysis and I'll answer your questions. If you have any questions, please take notes of them and we will get back to you. Okay, so the break, I think 15-minute break should be fine. So we will come back in 15 minutes. That's 7. Okay, there's a question. What does the second F mean? Sorry, what do you mean by second F?
Just now you typed in some instruction for us to follow as a report. So the first line, I just quoted a part from the first line. Yeah, this one.
Okay.
The first line, Hugh felt F estimates. Yeah, here.
Okay.
The first line. Yeah.
Okay, I see what you mean. This one and that one. So these F estimates refer to these Fs. You see, if we have, let me say, if you look at the estimates for greenhouse geyser, we have an F estimate here. Can you see that?
Oh, okay.
And if you look at this one, we have an F estimate here as well. And if you are curious how these are estimated, well, it's basically the mean square. Can you see that?
Yeah.
The mean square divided by the mean square of the error. So if you divide 103 times 578 over 19,364, you should get this value, this one actually. Can you check? I mean, there should be something very similar to this. Can anyone check that, please? So anyway, the F values refer to this F value here. And sorry, I think I made a mistake. This F value here and this one. Because it's Huynfeld, F value, greenhouse geyser, F value. That's what I mean. Is that fine?
Yeah, and since they are the same, so what's the point of choose this from three of these three?
Yeah, very good point. Well, basically, in some scenarios, they're not the same and makes a big difference which one you choose. So those criteria are stated there for us to always follow. Sometimes, like this scenario, all F values are the same, but in many other scenarios, they're not. Okay, so just follow the epsilon rule that I mentioned before, if it's smaller than 0.75 or if it's larger than that. Okay. Now it's time to move to this data set. Does everybody have access to it? Okay, so I'm going to start and run an analysis on time 1, 2, 3. Analyze, linear, general linear, repeated measures. I have time. Like I said, the name doesn't matter. 3 add, so I just remove that one. So I've got 3 time points, time, and define. So I'm going to move, reset it, time 1, 2, 3, 2, time 1, 2, 3. For contrast, I'm going to keep it as polynomial. So it will show me the trend, remember? Then I don't have, okay, plots. Let's do a plot. Let's get time. Post hocs, I don't have anything because I don't have any between subject factors. EMM means, let's do it. All of them, Bonferroni. Continue for save. You can do save standardized and then continue. I'm not going to do that, but you know what to do. You can look at the normality that way. Options, effect size is important so far. I don't check homogeneity. Again, because I don't have any between subjects factors. So effect size. So it's good. We can continue. Let's see what we got. Okay. Now, the scenario changes here. If you look at Mauchly's test of sphericity, is it violated or not?
Violated.
Because?
Because the p-value is still smaller than 0 to, oh no, it's larger.
Oh,
It's larger, I'm sorry.
it's not.
It's not violated. It's met.
Therefore, we don't need any
correction.
We don't need any correction. Let me close this. We don't need any of these corrections. Okay, so what do we do instead? Just before I go ahead now, as I go ahead, I give you slightly more details, increasingly more details. You know what is corrected is basically degrees of freedom. So you see that we have 3 time points, right? Time 1, time 2, time 3, right? So what is the degrees of freedom for that? Do you remember? 2. How do you know that?
Total group minus 1.
Exactly. Number of times here, minus 1. So I've got 3 times, 3 minus 1, 2. That's degrees of freedom. And you can see that degrees of freedom in the within subject effects has been corrected for, and we have 1.892. This is what correction means. The degrees of freedom are corrected for. This is a little bit of detail if you are curious. What do we mean by correcting? We correct the degrees of freedom. Why? Because if this is significant, which was in previous scenarios, then the F values here are not reliable. By contrast, if sig is not statistically significant, which means that Mauchly's test is fine, Mauchly's test of sphericity is fine, that is, Mauchly's test of sphericity is established, okay? So we don't really need this anymore. We don't really need this anymore. What do we need? is this table. So to help you visualize, look, much least test is situated between two other tables. This is for you to create a visual mental imagery of SPSS output. Okay, it's another way. So we have much least test here. Let me look at myself to see if my gestures are correct. Okay, I can see myself. So much least test is right in between. Multivariate test is there. Within subject effects is at the bottom, right? Okay, so much least test will tell you whether you should look at the one on top or the one at the bottom. You can take notes of that. Okay, so much least test tells me whether to look at the table which is on top of it, or look at the table which is at the bottom of it, immediately at the bottom. How? How? You should be able to answer now. I'm waiting for my answer.
To see the p-value or significance of the Maclaurin output.
Yeah, can you elaborate more? You're right, you're on the right track. So elaborate more, please.
So first look at the Maclaurin's test of sphericity to see if it is supported. If it's the assumption is supported, so just look at the table above. If it's not, to look at the table under it.
Very good. In this case, where should I look?
Oh, in this case, we should look at the above.
Multivariate test.
Multivariate test.
And that's simply because the significant or the p-value is larger than 0.05. So if it's larger than 0.05, look above. Larger, look above. Smaller, look below. I think it makes sense, right? Larger, look above. Look up. Smaller, look below. That makes sense. Okay, so in this case, we simply report the results of these tests. Now you're asking me which one to report. In some scenarios, the F values that they calculate for us are the same, like here. So in this case, it doesn't really matter. Partial eta squared is the same. The values are different, but that doesn't matter. What matters is the F value and partial eta squared. Okay, all of them show you the same sig value. Now, this is how you report it. Instead of this, now you should report it in a very simpler way. I don't know if you will consider that simpler. This is a sample. I'm gonna wait for you to read it in this one. I mean, only up to here. Okay, guys. So instead of this, we should check. Maclaurin's test was adopted to evaluate this and that. Sphericity assumption was met. So this should be corrected here, because in this case it's met. So, and instead of this part, what do you use? A sentence like this or similar to this. I mean, be innovative. Now, Wilks lambda is very commonly used. It's robust. You can either report a Pilate's trace test or Wilks lambda. I mean, either will be fine. As you go down, like Hotling's trace and Roy's largest root, they can get a bit less robust. So it's very common to see these two. Of course, there is more detail to this. I mean, I will try to share with you, but not in this session. I don't want to bombard you with a lot of information in this session. But currently, let's stick with this. Take it as a rule of thumb. Okay, rule of thumb, not a golden rule or anything. So that's in case Mauchly's test is not significant, is larger than 0.05. We look up. It's smaller than 0.05. We look down. Let's continue our analysis. I'm going to do something very interesting. Okay, this is what we have done before. Now, I have another variable, which is SES. Some of my students are from SES1, whatever it is. I mean, it doesn't matter. Some are from SES2, some are from SES3. This is a very small sample, by the way. Remember that. So I'm going to move SES to between subjects because I want to see what if I create 3 lines instead of 1 line. SES1, 2, 3. Does it change in any way? Do I have different patterns across the 3 SES levels or not? Remember that between subject factors should be nominal or ordinal. Nothing else. Nominal or ordinal. Okay, so far, guys? Now, what I would like to do is to go back to contrast. For SES, I don't need a contrast. Let's not make our life difficult. Plots, now I can have a lot of interesting plots. Time, SES, I'm going to remove time. I'd like to have SES on the horizontal line, time on the separate line. Or you could do it the other way around as well. Doesn't matter. This way, this way. So in this case, you're going to get 2 separate plots. It's just, you really shift the variables around. It's not a big deal. It's visual, so it may not give you a lot of information, but it's still cool to have a visual, visual information. Post hoc. Now, finally, we can post hoc analysis, SES. We have a small sample. The sample size is normal. Sorry, the data is hopefully normal. So I can use Tucky, not a big deal, and continue. Please look at the notes that I sent to your WhatsApp today. You can choose a better one. Take a look at the notes. They will give you more information. EMM means, okay. Now, should I do EMM means or not? Since I'm doing post hoc analysis, let's not confuse you for the time being, okay? I don't do EMM means now. Just want to do a post hoc analysis. So you remember, we either do post hoc or EMM means. For this analysis, I just want to show you that you can do a post hoc. Okay. Now, look at the results and tell me what I should do. Can you open your microphones?
Yeah, we should look at the above chart because the p-value is this specificity is mapped. Then we look at the chart above.
Exactly. Very good. So guys, look at the p-value here. It's greater than 0.05. So Mauchly's test of sphericity is met. Next, it's not violated. It's greater than 0.05. So next we look at multivariate tests. We do not look at these. So p-values, what do they tell you? Could you write a sentence for reporting this, please? I'm going to give you a minute. Go ahead. Okay, who is going to read it? Can someone who has never talked, or today has never talked today, can you open your microphone, please? I'm waiting.
Dr. Vahid, sorry, can I just ask, for the post hoc analysis equal variance assume, which is the name that we indicate under for this analysis?
Sorry, say it again.
Sorry, yeah, for the post hoc analysis, under equal variances assume, which was the one that we had to take earlier?
Post hoc analysis.
Was it Taki or?
Okay, so you're
Okay.
saying.
So it's just Taki, is it?
Okay, if you're interested, you can do Games Howl. Games Howl is very powerful. I suggest you can use this.
Okay, thank you.
Sure. I didn't do it because I didn't want to output too many data, so it will be confusing, but you can definitely choose it. So since you're now asking questions, can you tell me what you wrote?
Oh, sorry, I just got the analysis because I wasn't sure which one to pick under post hoc.
Okay, so
yeah.
Guys, if you have written something like this, it will be fine. Multivariate test demonstrated that the main effect of time was statistically significant. And then provide this. Of course, you should also provide what after this?
Like eta square.
Partial eta squared.
Partial eta square.
Yeah, they're different, by the way. Eta squared is different from partial eta squared. So partial eta squared, very good. Now, the effect. Now, I want to go ahead and now look at the time and SES. We have an interaction now. What does it mean? It means that I wanted to, let me visualize it. Actually, it has been visualized already. So let's go down like this. You see, instead of having one time, I have 3 time points. So for, 3 time graphs. For SES, okay, here, this is better. For SES1, what color is the graph for SES1? It's the blue one, right? So instead of having one graph, I've got 3 graphs. So this is what I mean by this line. The effect was not qualified by any time-gender interaction. Of course, in this case, let me see if it's qualified or not. Time SES, is it? Do we have an interaction?
No,
No,
we
because?
because
Its
the
value is larger.
significance is larger than 0.05.
Good. So here, what do you write? Do we say it was not or it was qualified?
It was not qualified.
Exactly. It was not significant. So it was not qualified by any time times SES interaction. Then you provide the Wilks lambda or Pillai's trace test, followed by partial eta squared. You should spell it out and you should write it down. Any questions? Okay, I see a question.
Where does the 84 come from?
The multivariate test. Okay, this is good, yeah. You think this is good. Sorry, someone asked a question or something else?
So we're going to report Wilkins lambda equals to this one, 0713, and then with F value, the equals to something, and in that bracket, you write down in the previous PPT you just shown, yeah, here's 3 and 84, but I don't see any 84 in the table.
Precisely. Actually, that was my next question for you guys. I was going to ask you, can you find the error in this statement, which you already found? You're right, that's an error, so it has to be 26. Good job. Okay, any other questions? No, that's good. I mean, it's satisfactory to see you guys can identify errors and all that. That's pretty good. So, group work. I would like you to run 2 analyses. Let me go back. Here. We have got time 1, 2, 3, test 2, 1, test 1, 2, 3. So we have 2 independent variables, time and test. Are they within or between subjects?
Within.
Sorry?
Within subjects.
Within subjects.
Good. And we have 1 between subject variable, SES. Now, I would like you to do 2 analyses and write 2 reports.
Do we use post hoc or EM means?
Okay, I would like you to use EM means this time round. Okay, analysis 1. Find out whether there is any significant difference across time 1, 2, 3. And if there is there any interaction, sorry, between tests, test 1, test 2, test 3, is there any interaction between test and SES? That's analysis 1. Okay. Analysis 2 is more complex. And this time round, instead of having 1 factor or 1 within subject variable, we're going to have 2 within subject variables. So in the windows here, you should define 2 of them. One of them is whatever add, the other one is, so one of them is test, the other one is time. When you go to the next table or next window, you will see a little bit of difference. I'm sure you can figure it out. So I would like you guys to do these 2 analyses. The second analysis is more complex. It has got test and time as within subject variables and SES as between subject. For both, use EMM rather than post hoc. I'm going to give you, this is a very important question for me, and if you can manage to answer this, I will be very happy. I can sleep well tonight. So I'm going to give you around 25 minutes, should be fine. Is that fine, or do you want more time?
30? What about 30 minutes?
Okay, 30 minutes. Okay, no problem. This is 30 minutes. Also try, since I'm giving you 30 minutes, also try to write a report if possible. So one of you should be responsible for writing the report. Okay, so I'm gonna get you back to your breakout rooms. Everybody, 30 minutes will start from now. Please go to the rooms. Sorry for pulling you back. I don't know if you finished it, but I looked at the time and saw, gosh, we should finish this session. So I don't know how far you have gone with the analysis, but what I'm going to do is to do a quick analysis for you to show how it's done. General linear model, repeated measures. So we have test, right? There are 3 tests. This is just for the first analysis. And define it. I'm going to move test 1, 2, 3 to this side. I'm also going to move SES here. This is what you have done, I assume. Contrasts we can do for tests. Let's do a plot as well. SES versus test. Add. Continue. EM means. The EM means. I'm going to get all the EM means to the side. Compare main effects and Bonferroni. Continue. I don't want to save, but you know what to do. You can save standardized. I don't, because you know the procedure. I'm going to do estimate of effect size. Now, since I have a between subject factor, I can check for homogeneity. So sphericity is for the repeated measures part. Homogeneity is for the between subjects part. And we have 3 levels. So I think that's just good enough for us. So let's click OK. And there we have this output. Okay, guys? Now in this output, we have an additional variable. That's equality of covariance matrices. So in addition to Marchli's test, we have another one. Do you know the reason? What I would like you to add here, I mean, to keep it in mind or just add it somewhere in your notes is in this note, you should include, where's my pen? I think I lost my pen. Anyway, so number 4, we have already included that, equality of covariance matrices between groups. This appears whenever you have a between groups subject variable, and that's, again, let me remind you of it. This is the between groups variable, SES. You see, between subjects, and this appears here. It compares them across groups. Okay, so I don't want to over-explain it. Whenever you have that variable, this will appear, equality of covariances. How should we examine this? This should, I don't know if I haven't written it here, but it's like the usual analysis. We should look for the p-value, the first in the first place. If the p-value is smaller than 0.05, just like Marshall's test, it's violated. If it's larger, it's good news. So this is good news now. Okay, so you can say the box is the name of the person who created it. Test of equality of covariance matrices showed that this assumption was met or was established that provide the p-value. If you like, you can provide the degrees of freedom 1, degrees of freedom 2, close the brackets, f equals 0.707, and then provide the sig value. That's another way of reporting it, just pretty much like other tests. Okay, so far? So you first report this. Now here, do I look at multivariate tests or within subject tests?
Within.
Good, because?
P-value is
smaller than 0.0.
Smaller than 0.05, so I should look down. Look at the table below it. Now, which one should I look at? Greenhouse geyser?
Yes.
Yes.
Greenhouse geyser.
Excellent, and that's because greenhouse geyser is smaller than
Smaller
0.0.
than 0.75.
Excellent, and I look at this, is this significant?
Yes.
Yes.
Partial area square is huge. So there's a significant effect size for test. That is that the scores significantly change across time. And you know how to report it. I've explained it before, so let's not talk about it. And now, is there a significant interaction?
No.
No.
How do you know?
P-value
is larger than
0.05.
Okay, Liang Li is asking how to understand quality of covariances. So I don't think I'll find time today, but anyway, so there are covariance matrices for each analysis, and you compare the covariance matrices across the times. Again, it's based on algebra and vectors, the comparison of vectors and algebra. I think that's perhaps everything that we need to know for running the analysis and making sense of it.
And for the covariance, not variance.
Yeah, it's covariance, is the covariance of the variables. How do they co-vary with each other? If one of them goes up, would the other one go up as well or not? So it's covariance is the non-standardized correlation. Correlation is a standardized covariance. So you want to see if the correlation matrices across time are significantly different. And it's not done, it's not really easy to do it step by step in SPSS because it takes quite some time to make sense of the algebra underlying it. But generally speaking, it's like comparing correlation matrices of time 1, time 2, time 3. Correlation of the variables with each other. So, okay, so let's move to this one. We said that there is no significant relationship interaction between test and SES because of the p-value. Good. So at this time, we can move down to okay, let's assume that SES and test had a significant interaction with each other. Let's assume. In this case, because we are looking at the relationship between SES and test, and SES is a between subject variable, and it's an ANOVA, so we should have looked at the Levene's test of equality of variances and based on means. So for test 1, test 2, test 3, there will be one Levene's test generated. In this case, none of them is significant. So the assumption of equality of error variances is or is not assumed.
It's
is met. Good. It's like Maclaurin's test because it's larger than 0.05. So we don't need it now. The reason is, just like I said, the interaction between test and SES is not significant. Okay. And sorry, I go through this a bit faster than usual. You can pause the video later when I upload it and watch it. And next session, we will review everything again. This is the end of multivariate analysis in this course. So that might be good news for some of you. The next session, we will review everything again. So we need this only if the interaction analysis is significant. That's something that you can put down. If it's not, just leave it as is, forget it, ignore it. And now we want to look at the, so you can ignore all of these. Look at the estimated marginal means. Okay, so we are looking for SES. SES is number 2. We always look at, I mean, SES was not significant, so you can leave it as is, because anyway, it's not significant, as you see here. Can you see? Now, what matters is test itself. So test, as you see, there are significant differences. Is there a significant difference between time 1 and 2?
Yes.
How do you know? Because of the p-value, right? It's smaller than 0.05. 1 and 3. I'm waiting for your answer. 1 and 3?
Yes.
Good.
Yes.
Yes.
2 and 3?
Yes.
Yes.
Very nice. Now, is our trend linear or quadratic? Let me see if I can find that. Here. So test itself, is it linear or quadratic? It seems to be both, right? So in this case, it doesn't matter which one would be chosen. And the reason why both of them are significant is that we only have 3 time points. The more time points we have, the more reliable this analysis would be. In this case, what you can report is the trend fitted both linear and quadratic. It's not possible to decide which one is better because we only have 3 time points. However, based on the partial eta squared, it seems that the linear model provides a better representation of the data. Can you see that? So temporarily, we can say that the model is probably, the trend is probably linear. So it linearly goes up, generally speaking. But this one is a little bit of an exception, but this is not very important because SES was not a factor anyway. So what I would like to remind you is that we should provide evidence of these 3 and then report the results in the same way I mentioned before, in this way. Okay, so it's the same. It's just the only thing we're adding is equality of covariance matrices. Now, I know that all of you are eagerly waiting for 9 o'clock to go home. I mean, you're home just to take a rest. What I want to do is to quickly run the last analysis for you, and I will follow up on this next session. I think I might have given you slightly, I mean, the wrong kind of information here. I apologize for that. I said that you need to put in the data here, right? But actually, let me reset everything for you. Actually, you need to put it here because we have 2 measures, test and time. So the measures names go here when you have 2 measures. So test, time, added in. Now, we still need a factor. I mean, you can call it whatever, because it's 3 times. Time 1, time 2, time 3, test 1, test 2, test 3. We're measuring some factors there. So let's call this factor just factor. I don't know what it is, honestly. So let's call it factor. There are 3 time points for that factor. This is how it is measured, okay? So then define, and this is what you should get. So time, because of the information, I know you have probably ended up somewhere else. So let's start from time 1. Time 1 goes here. You see 1 time, right? Okay, so I think we should start from test 1. Okay, test 2, test 3. This is the best. Time 1, time 2, time 3. And the rest of the story is going to be the same, but I'm going to quickly finish it for you. SES, between subjects factor. Contrasts, we can keep factors as no polynomial. Continue. Plots, maybe these 2. You see the plus doesn't change, it's just within subject across between subject. We don't want to have post-hoc analysis, as I mentioned before, because we can do EMM. And why not doing EMM? Okay. Continue, options, save, homogeneity test. You all know these steps, okay?
Dr. Vahid, can you also click the save to do the residue normality check, because I couldn't get through their part for this step.
Okay, so standardized, okay. I go back to the data. You see we have got residuals for each of the variables.
Yeah.
So you can run a quick analysis since you're asking for it.
Yeah, I did the same, but this residue doesn't show.
Oh, it should. I'm sure it will if you do it correctly. So this is how it, oh, I forgot to include, anyway, I forgot to include, I forgot to check skewness kurtosis. Anyway, so let's go back. Okay, is this met or not? Yes, it should be more or less the same because we're just focusing on SES.
No.
The box test of equalitative covariances is met. Now we should look at Mauchly's test. So Mauchly's test has been generated for 2 variables this time around. For one of them is test, the other one is time. Can you see that?
Time is met.
Time is met. So for time, we can, for test, we should look at here. Yeah, for time, we look at here. So let's continue this next session, guys, because it's getting late. But keep this in mind. Next session, we have plenty of time to do the rest of the analysis. What I would like to remind you is, please don't miss your deadlines, because NIE has become stricter about it, and I'm afraid I may not be able to help you. If there is a late assumption, I have to report it. So it's beyond me, really. So I hope that you will understand that and will not skip your deadlines. So it's pretty late, but I can take one last question if you have any.
Sorry, Dr. Vahid. So I have a question about the reporting of the table. So if there's no significant effect of the interaction of the variables, do we need to still report that?
No, you can just say there was no significant interaction.
And do we need to provide the F value and the P value as well?
It would be much better. I highly recommend you do so. Yes. Yes, please do so. Yes.
Okay, thank you.
You're welcome. Anything else, guys? So
sorry, I have a quick question about the table of the contrast, like the liner and the, yeah. So how, I might miss some points, but how can we decide if it is a liner or I think we just missed that part.
So sorry, what is the question again? Contrast and what
yeah,
about
the contrast. So how can we decide it is a minor or the other way?
It is minor?
Linear.
Oh, it's linear. Okay.
Linear, sorry.
And it's linear or quadratic because of the significance.
Exactly.
Yeah,
Look at the
so,
p-values. Let me go back to.
Not, I think, yeah, I think
Where?
we just.
It's further down, but let me look at the previous one. It's straightforward. Anyway, we can find it here. Multiple test, pairwise comparisons. There's so many outputs here. Can you imagine if you had to do this manually? Sorry, I go back to the previous contrast. If I can ever find it. So the point was that linear, nonlinear contrasts both applied. This is not that was the trend. Come on. Okay, here. Let's say this one, right?
Mm-hmm.
Because both p-values are significant.
Yeah.
So the question is, which one is the best? It's very difficult in these scenarios. It's very difficult to say which one is the best. Why? Because we only have 3 time points.
Mm-hmm.
So when you're looking at trends, we should have a lot more time points, maybe 10 time points or more.
Yeah.
I'm just guessing 10 is not the golden number. But here's the thing, my hunch here is that since the partial eta squared for the linear model is higher, 0.757, whereas the other model is quadratic, has got a lower partial eta squared, my hunch is the first model is better. Why? Because it explains more variance. So I wrote a word before, curve fitting, right? In curve fitting, you look for a model that best explains your data. And here we have some evidence that linear is the best.
Yeah. Okay, so if for the
So first
p-value,
look at the p-value, then look at the partial square as a tentative solution.
okay, so for the p-value, if the linear is significant, so we can report that it is a linear
Yeah,
chain.
you can say it's linear.
Why do we need to report if it's linear or not, or quadratic? What's the practical meaning for that?
Yeah, it's because we have got, I mean, in a sense, you can call these time series or longitudinal data. When you have longitudinal data, you're thinking about a trend. And a lot of people would be interested to know, what is the trend? Is it this way, linear, or is it nonlinear, curvilinear, quadratic? So they wanted to imagine the shape of the trend.
So it will not happen that both linear and quadratic are significant, right? So only one of them is significant.
Well, in this scenario, both are. Can you see that? Look at the p-values. So now we should prefer one of them.
Okay.
Because it doesn't make sense to have both quadratic and linear.
If it's not so obvious, do we still need to report the trend?
What do you mean by not obvious?
Yeah, just like this one you just used, because it's limited in the time, it's 3 times.
Yeah, I suggest you do.
Still.
Yeah, I suggest you do. You can't just say, oh, it's not, so let's forget it. But it's important because always remember the question of reproducibility. If someone in the future implements a research study like mine, can they find very similar findings or no? So the more information you provide, the better it is.
Oh, okay. So can I have one last question? Then what's the point about reporting that just a covariance equality?
Well, that's an assumption. You have to box covariance.
Yeah.
This one, it's another assumption. It's like Levine's test.
It's not in the PPT yet.
Oh, it is. I mean, there's quite a little bit about it.
Oh.
If you look at this one.
Oh yeah,
box.
But on the report, I mean.
Sorry.
Oh, okay. I just mean not on that page. You just showed that report.
Also, report, just innovate. I mean, you should be able to now generalize whatever I have said to this context. It's very easy. It's just like a t-test, or like an f-test. How do you report f-tests? It's exactly the same way. Also, I just mentioned it a few minutes ago. You can review this video and see how you can report it. So, guys, everybody is sleepy. I can see that some of you are just like.
As about writing critique, what should we focus on? Do we need to focus on the way the researcher analyze the data?
Yes. Yes. If you want to critique a paper, you want to see what they have done and what they have missed. So you should report that. So they did this and they did it well or no, and they missed on this and that, and this is the problem, or this is the limitation. They should have done this, they should have done that, they should have done that, like that.
Do we need to report some information about how this author designed the experiment?
Yeah.
Yes, please.
How they do grouping, sampling.
Yes, that's important too, because we have covered all of those. Everything covered in this course. And there's a reason why we have covered them based on previous research. Those are very important. So I have intentionally, I have selected them to be a part of the course because I want you guys to familiarize yourself with those concepts and look for them in papers that are published. Okay, guys.
What? Just one moment. But if the box test is met, what's the next? So we should look at which table?
So you just do the same thing as mentioned. So this is met. Then you go down and look at the Mauchly's test and the rest of the story after Mauchly's test of sphericity.
So it's before Mauchly's test.
Yes. Okay. And it's only for the between subject variable.
Okay.
Okay. So if you have questions, we will be able to answer them next week.
Are we coming back to class next week?
Sorry?
Are we coming back to class next week?
I'll let you know.
Okay.
I'll make an announcement about it. Okay. Thank you, everybody.
Thank you.
Goodbye.
Thank you. Goodbye.
Bye-bye.